Hello, my name is Ayman Al-Hajjar. Welcome to Security Informed Safety. This is the second lecture, which is part of the Safety Informed Security lecture series for CyBOK. In this lecture, we look at security informed safety as an assurance problem. The question is no longer simply, is the system safe under expected failures? The question becomes, can you still claim the system is safe when an intelligent attacker can compromise the components, networks, or assumptions on which safety depends? By the end of this lecture, we should be able to explain why attacks are different from accidental failures, describe how a security breach can become a safety hazard, understand the role of safety cases and CAE arguments, and explain how security threats can be integrated into safety risk assessment. This lecture mainly mapped to the CyBOK cyber-physical security systems knowledge area. That is because the focus on the systems where computation, communication, and physical process interact. It's also partly linked to risk management and governance because we are discussing assurance, risk, and evidence. It's partly linked to adversarial behavior because the lecture introduces attacker intent, strategic behavior, and adaptive attacks as part of the safety argument. The point is that security-informed safety is not only a technical topic, it sits between system engineering, risk management assurance, and adversarial reasoning. We're going to first revisit the convergence problem and the causal chain from breach to threat to hazard. Then we're going to define the security-informed safety concept and explain why attacks are not the same as failures. Third, we examine these three case studies where security weaknesses create safety-relevant consequences. And then we introduce safety cases, claims, arguments, evidence, and goal structuring notation. We then show how security can be integrated into safety risk assessment and hazard analysis. And finally, we discuss common mistakes, practical challenges, and regulatory drives. So let's start with the core problem, the convergence problem. Security protects assets from malicious interference, and safety protects people from harm caused by system behavior. In older systems, these concerns were often analyzed separately. Security was about data and access. Safety was about hazards and failures. In connected systems, that separation no longer works. A security breach can directly cause a safety hazard. For example, if an attacker compromises a building management system, the result is not only unauthorized access to a network, the result may be unsafe temperature control, poor ventilation, disabled alarms, or unsafe access control. The problem is therefore an assurance problem. How can we claim a system is safe? If attackers can compromise the systems, it depends on. This question is central to the rest of the lecture. So, if you look at this basic causal chain of breach to hazard, a security vulnerability creates an opportunity for an exploit or an attack. If the exploit succeeds, the system may become compromised. Once compromised, the system may behave in ways that create a safety hazard. And if this hazard is realized, harm may occur. The example on this slide uses a building management system. An unauthenticated MQTT broker is the vulnerability. The attacker exploited by publishing false sensor data. The building management system then displays the wrong temperature. That wrong state may cause the HVAC system to shut down in an occupied building. The resulting harm could include heat exposure or even respiratory distress. And the important point to make here is that safety harm is not caused directly by the attacker typing comments. It's caused because the attack changes the behavior of a system that people rely on. That is why security-informed safety requires us to trace the path from the security vulnerability to exploit, from exploit to compromised behavior, and then from compromised behavior to reaching the hazard. The next step is to understand why attackers cannot simply be treated as another kind of random failure. The core problem. Safety engineering. This is a traditional problem. Safety engineering assumes failures are independent and random. Attackers, in this case, violate both assumptions. For example, hardware components degrade sensor drift. Software defects appear under certain conditions. Environment conditions may create stress on the system. However, when the attackers violate these assumptions, a deliberate attack is not random. It's targeted, strategic, it adapts to defenses. It may deliberately look for common mode failures, where one action compromises several layers at the same time. The table that you can see contrasts accidental failure and deliberate attacks. In an accidental failure, the cause may be, for example, wear, defect, or environment. In a deliberate attack, the cause an intelligent adversary. In an accidental failure, redundancy often helps because failures are assumed to be independent. In an attack, redundancy may not help if the attacker compromises the shared dependencies that all redundant components rely on. For example, two sensors may be physically redundant, but if they both publish through the same unauthenticated MQTT broker, an attacker may spoof both data streams at once. The security safety consequence is clear. Protections against non-malicious failures are not enough against strategic attackers. This becomes especially serious when an attacker targets the mechanism that we are supposed to safely protect it. If you look at the protection or the layer of protection and where security fits, this slide shows a layered protection model where in many safety critical systems, protection is actually layered. And we may have process design, basic controls, alarms, operator interventions, a safety interlock system, a physical protection, emergency response. All of those are layered approach. The idea is that if one layer fails, another layer prevents escalation. Security changes the assumptions behind this model simply because an attacker may bypass or disable multiple layers. They may attack the alarm system. They may prevent operator visibility because the alarm is not basically being raised, manipulate the safety interlock, or compromise the communication paths that reports system state. If the attackers can target the safety mechanisms themselves, how do you justify that the system is safe? And this is not a theoretical question, it's an assurance question. We need evidence that the safety mechanism remain trustworthy under realistic security threats. That leads to the practical definition of security-informed failures. So if you want to define it, first, treat attacks as a hazard class. Security threats should appear alongside hardware failures. Software defects and human error in the hazard register. They are not an external entity to safety analysis. They are part of the conditions that can lead to harm. Second, include security evidence in the safety case. If a safety claim depends on sensor data being trustworthy, then the safety case needs evidence that the sensor data cannot be easily spoofed, modified, or suppressed. Evidence might include penetration testing, access control review, encryption verification, authentication design, log analysis, or configuration inspection. And third, maintain the safety case as a threat as threats evolve. Security evidence becomes stale. A penetration test from 2 years ago does not prove that the system is secure today. New vulnerabilities can invalidate earlier assumptions. Patching can also change the system and affect certifications. Security-informed safety, therefore, needs lifecycle thinking. The practical message is simple. Safety assurance cannot be a one-off document. If the threat landscape continues to change, we need to ensure that safety assurance also continue and evolve. So how do you put all of these in practice? From security breach to safety hazard. So let's look at the first case study. The first case study concerned implantable cardiac devices, for example, pacemaker, implantable cardioverter, defibrillators. These devices are safety critical because they monitor and affect cardiac function. Traditional safety analysis may focus on hardware reliability, fail-safe operation, and correct therapy delivery. However, there's a lot of demonstrations that wireless reprogramming could be possible without authentication. An attacker could potentially disable therapy, alter settings, or induce a shock even. And the safety significant is that a mechanically sound device can become unsafe because the security boundary is weak. The device may still pass many traditional safety checks, but those checks do not address unauthorized wireless control. So the safety question here is not only whether the device functions correctly under normal conditions, it's also whether the communication and programming interface can be trusted. The second case moved from medical devices to connected vehicles. The second case study is the 2014 Jeep Cherokee remote exploit. And here, the system included the Uconnect infotainment system. Cellular connectivity and access to the vehicle's internal network are part of it. The security finding was that attackers could exploit the vehicle remotely via the cellular connected infotainment system, pivot to the CAN bus, and affect steering, braking, and transmission. Obviously, from a safety perspective, this matters because the vehicle may have passed safety certification, but the remote network attack path was not treated as a hazard source. And the key point is that attack surface, a feature intended for connectivity and convenience, created a path into safety-relevant vehicle controls. And this is a strong example of safety impact, of why security must be considered during safety analysis. Otherwise, the system may be judged safe under mechanical and electronic assumptions while remaining unsafe under adversarial cases or conditions. And in the third case, which is even more direct because it involves attacker targeting a safety system itself. Here we have the third case study, Triton Crisis, when attackers target safety systems. Triton, also known as Trisis, targeted a safety instrumental system at a petrochemical plant in Saudi Arabia in 2017. The safety instrumental systems were designed to act as a protective layer. They monitor plant conditions and intervene when unsafe conditions arise. In other words, they're meant to be a final line of defense, basically. And in this case, attackers were able to access the operational technology network and targeted Schneider's electric Triconnect safety controller. The intent was to reprogram the safety system so that unsafe plant conditions could occur without the expected protective response. And this was significant because it showed that malware could be designed specifically to disable safety protection. And the security-informed safety lesson here is that safety system cannot simply be assumed trustworthy. It must itself be protected, monitored, and included in the threat model. So let's take these cases together, and to show these cases show the same patterns across different domains, right? So you have the Jeep case, the Jeep Cherokee case shows that network connectivity can create an attack surface that traditional safety testing may not cover. Obviously, the implantable cardiac device can show that safety analysis excluding security threats can produce a false assurance of safety. And the Triton Trices case shows that safety systems designed as the final line of defense can themselves become the target of the attack. Across all three cases, the core message is the same. Security weakness can invalidate safety assumptions. This is where the security-informed safety is not about adding a separate security checklist at the end. It's about integrating security reasoning into the safety argument from the beginning. And to do that, we need to understand how safety arguments are structured. And a safety case is a structured argument supported by evidence. That is, the system is acceptably safe for a given application for a given environment. So what is a safety case? Safety cases are used in safety critical industry, for example, in nuclear, aviation, rail, medical devices, and defense. And a safety case is not usually just a checklist. It's not a simple pass or fail test. It's a reasoned argument that explains why the available evidence is sufficient to support the safety claim. The central question is, why should we believe this system is safe? That's what the safety case explores. The security-informed safety changes the answer considerably because we cannot answer it alone or only with failures rate, redundancy, and software validation. If the system is connected, we also need to account for security assumptions, attacker capabilities, and the trustworthiness of data and control paths. And to understand the gap, we need to look at how functional system and functional safety standards often frame failures. For example, functional safety standards such as IEC 61508 and IEC 61511 are central to the engineering of safety critical systems. And the IEC 61508 is a general functional safety standard for electrical, electronic, and programmable electronic safety-related systems, while the second one, the 61511, focuses on the safety instrumental system in process industries. And these standards define approaches for designing, validating, maintaining systems against failure. However, traditional functional safety approaches often assume that failures, as we said, are accidental and random. And this is the assumption gap. This is where the gap is. Traditional functional safety assumes accidental failures, not connected systems facing intelligent adversaries. That doesn't mean functional safety standards are irrelevant. Of course not. They remain essential. The problem is that their assumption must be extended when connectivity and adversarial behavior becomes part of the operating context. This assumption gap is closely related to defense in depth. In defense in depth, because we rely on layers of protection, the core assumption is that failures are accidental, independent, and random. If one layer fails, another layer should still operate, and redundant systems should fail independently, so simultaneous failures should be rare. That's the assumption. That's the core assumption. Under those assumptions, redundancy works. Testing helps prevent failure, and defense in depth provides the assurance that we need. An intelligent attacker, however, violates all of these three assumptions. The attack is deliberate, is targeted, it may intentionally create common mode failures. For example, an attacker might compromise the shared network, the shared credentials, the shared update mechanism, or the shared message broker. In that situation, multiple safety layers can fail together. And the safety case must therefore ask whether the independence assumptions are still valid under attack. So we now need a way to express safety claims and the evidence that supports them. The claims argument evidence is a framework structure of a safety case in terms of those three different terms. In this case, a claim is a statement about safety that needs to be demonstrated. For example, the patient monitoring gateway does not deliver false vital sign to a clinician. Obviously, this needs to be demonstrated. An argument, the reasoning that connects claim to evidence, explaining why evidence is sufficient. For example, all data parsers are authenticated and integrity checked. That's the argument why we're making that claim. And evidence consists of concrete artifacts that substantiate the argument. For example, TLS mutual authentication has been verified by an independent penetration tester. So we have provided evidence to support the claim so that the argument we're making is that all data classes are authenticated and the integrity check. The value of CAE is that it makes the structure explicit. It shows what is being claimed and how it's being justified and what evidence supports the justification. For security-informed safety, CAE is useful because it exposes unstated assumptions. If a safety claim depends on a secure network, then the network must appear in the argument and be supported by evidence. Let's have a look at an example of CAE. We have a claim. In this claim of a structured informed example, basically, a gateway delivering accurate vital signs. The claim is decomposed into security relevant subclaims. So we have the claim of gateway delivering accurate vitals, and it's divided into several different subclaims. Data integrity preserved, source is authenticated or must be authenticated, no unauthorized publishing of data. So unauthorized publishing should be or must be prevented. And each subclaim is supported by evidence. How are we providing this? For example, for data integrity preserved, 8MAC on MQTT payload may support the data integrity claim. TLS clients may support source authentication, or broker ACL configuration for access control and testing may support the claim that unauthorized publishing is prevented. However, the important point here is that the safety claim depends on security evidence, and if the evidence link breaks, the subclaim is unsupported and the top-level safety claim fails. For example, if the MQTT broker has no access control list, the subclaim is unsupported and the top-level safety claim fails because obviously this fails, so the top-level simply fails. And this is exactly the type of gaps that security-informed safety is meant to reveal. So the goal structuring notation, or GSN, which is a graphical notation to represent the safety cases. In GSN, a goal corresponds to a claim. A strategy corresponds to an argument or reasoning used to decompose the nodes, to decompose the goal. And a solution corresponds to evidence. This is where the evidence will be. Context nodes capture assumptions, scope, environmental conditions, and undeveloped nodes show part of the arguments that are not yet complete. And GSN complete the case, the claim and arguments and the evidence, simply because it makes the safety argument visible. It shows where claims are supported, where evidence exists, and where gaps remain. For security-informed safety, GSN is especially useful because we can mark security assumption explicitly. For example, a context node might state that the IoT sensor communicates over MQTT on Wi-Fi. That immediately raises a question about Wi-Fi threats, spoofing, interception, availability, and so on. Let's look at how we can apply this to a simple IoT building management system. So we have the GSN example of an IoT building management system where the top level goal is that the building management system, BMS system, does not create unsafe environmental conditions. The context is, of course, that IoT sensors, they communicate over MQTT on Wi-Fi. That context matters because the safety claim depends on the network sensor data. Now, the strategy is to argue over each threat to sensor data accuracy. We look at those threats, so you can put sub-goals to prevent all of those threats. And the threat here to sensor data accuracy can be spoofing, can be intercepted, or can be the data being tampered with. So they must arrive reliably. So our strategy here, we need to make sure that the sensor data is not spoofed. We need to make sure the sensor data is not intercepted, and we need to make sure that the sensor data arrived reliably. The first two sub-goals are supported by evidence. You can see here, MQTT is authenticated, broker access control is tested. The second one is about not intercepted. Even if it's intercepted, it cannot be compromised because it's encrypted. And that means that they can hear what's happening, but they cannot understand what it contains, the message. What's undeveloped is the sensor data arriving reliably, which means basically sensor data is marked underdeveloped because the argument is incomplete. Availability analysis is still required before the safety argument is complete. And a visible undeveloped node is not actually a failure by itself. It's better than finding the gap. So it's good that you find something that is undeveloped rather than hiding the gap, and then the problem becomes bigger and becomes a safety hazard when the compromise happens, or when an argument is ignored or forgetting. This is where it becomes dangerous. So the next slide, we're going to summarize what makes actually a good GSN argument. So usually when you're defining a GSN argument, you define the goal, which means what safety property must be demonstrated. That's a clear goal. And then you state the context, system boundaries, assumptions, environment, network, all of this. And then you decide on the strategy, how the goal is going to be decomposed into sub-goals. What are all of those sub-goals that achieve the ultimate goal that you set to yourself in this GSN argument? You support all of those sub-goals with evidence or decompose them further. You can decompose them further because sometimes even one sub-goal can have different parts. One part, for example, that is supported, one part that is unsupported. And you can mark what is supported and what is not supported. And the idea is the quality checks are very important. Every goal should be supported. Reasoning should be explicit. And evidence is verifiable. That's why a good GSN argument has those. Goals that are supported, reasoning that is explicit, and evidence that are verifiable, and assumptions that are all stated. And in security-informed safety, many weaknesses arise simply because assumptions are not stated. For example, a safety case might assume that the wireless link is trustworthy without saying so. Once that assumption is made explicit, then you can challenge it, and you can provide evidence if that's the case. We then talk about how assurance break when security is missing from the argument, or why assurance break. Consider a traditional safety case for a patient monitoring system. The claim might be displayed vital signs are accurate. Traditional evidence might include sensor calibration, hardware redundancy, and software validation. All are showing that there is no reason for the vital signs not to be accurate. These forms of evidence are useful, but they may miss a critical issue. What about the wireless link? What if the link is spoofed? What if an attacker injects false MQTT messages? If the safety case does not address those questions, then it contains an unstated assumption that the communication channel is trustworthy, which is not the case, or which can be not the case. That is the assurance gap. Unstated assumptions create exploitable gaps in the safety argument. And this is one of the most important ideas that we're covering now. Attackers often exploit assumptions that engineers did not make explicit. So let's look at the assurance argument to risk assessment. How you integrate security to provide assurance into the safety risk assessment. A simple risk model defines risk as the likelihood multiplied by the severity. That's the traditional safety risk, where likelihood from failure rate, for example, the mean time between failures, and measure severity in terms of harm to people. Mitigations usually include redundancy, fail-safe design, maintenance, and so on. And security risks are different because security risk is about likelihood depending on attackers' capabilities, opportunities, and motivation, and it's not statistically predictable in the same way as a random hardware failure. Mitigations include access control, encryption, monitoring, authentication, and incident response. And security-informed safety risk combines both. It considers hazard sources, safety consequences, and the security controls needed to keep the mitigation trustworthy. The central change here is that severity must include safety consequences, and likelihood must account for adversarial conditions rather than only random failure rates. And that leads us to the threat model, or the extended threat model. Security-informed systems requires considering all failure cases, including malicious attacks. If you look at this example here, this table, you have the failure types, characteristics, and safety implications. Malicious attack is, if you think about random hardware, can be statistically modeled and handled by redundancy or random failure of hardware. Software defects are systematic and repeatable and can be handled by testing and verification. Human error is probabilistic and context dependent. So we use, for example, interface design, training, and procedures to provide the to reduce the human error. Training and procedures are part of the human error. However, environmental causes can be addressed using sensors and monitoring. Malicious attack is different. Malicious attack is intelligent, adaptive. It's not handled by traditional methods alone. That is why malicious attacks require new methods, new evidence, new expertise. The point is not to discard traditional safety methods, as I said before. The point is to extend them so that the deliberate attack is treated as a credible cause of unsafe system behavior. So we can basically put this into a practical analysis process. Traditional hazard analysis is extended by explicitly including security threats. And here we have this 6-step process by identifying safety critical functions. First, there are functions that are displaying patient vitals, controlling HVAC, or delivering therapy. Next, we move to identifying the data and control paths supporting those functions. This includes sensors, network, gateway, controllers, actuators, and so on. And then we ask for each path, what if an attacker can read, modify, block, or inject data? What would happen to the data? What would happen to our system? After that, we assess the safety consequences of each attack. This should use the severity category. This is like risk assessment, but safety consequences for each attack. We're looking at the severity of categories for safety standard where possible. We're using the safety standard if possible. And finally, we identify security controls that prevent or detect the attack. For example, authentication, encryption, access control, monitoring, and so on. And obviously, finally, document the results in a safety case, because it's all about documenting so that security control claims become part of the assurance argument. And this process makes the security safety link concrete. Let's have a look at this idea in a smart MQTT sensor. If we look at the 6 steps, the critical function is temperature monitoring for HVAC control. That's a traditional safety. And security informed is the same. The data path is sensor, wired, and the building management system. In the security informed system, the sensor, Wi-Fi, MQTT, and the building management system. That means the communication path is now part of the analysis. The hazard is not only sensor drift or failure, it also includes spoofed MQTT messages. Consequences is not only operation on stale data. The HVAC system may act on false attackers' controlled data. And the mitigation, therefore, cannot only include calibration and redundancy. It needs to also include MQTT authentication, TLS, broker access control, and so on. So the security safety shifted in that the wireless and the MQTT path is not just a communication channel, the path. It's part of the hazard analysis. And that's what matters. Let's look at another example where we apply the same 6-step process to the implantable cardiac device case. So the safety critical function is delivering defibrillation therapy when cardiac arrhythmia is detected. The relevant data and control passes include the sensor to RCD logic, the RCD logic to shock delivery, wireless, and the wireless programmer to RCD configuration path. And this is the path of the data on the control. The attack possibility is an attacker can reprogram the RCD, the implantable device, through an unauthenticated wireless interface. They could disable therapy. They could alter threshold or even induce a shock. The safety consequences could be patient death if therapy is disabled during arrhythmia, or induced fibrillation, or if the device is manipulated to do all of those. Security controls include mutual authentication, encrypted comments, and proximity-based access. The safety case entry might be no unauthorized reprogramming is possible. Evidence would need to support that claim, for example, penetration testing and authentication protocol verification. And this shows how a security threat becomes a part of a safety analysis framework, rather than being treated as a separate IT issue. And let's have a look finally at the common mistake, challenges, and regulatory drivers. So, there are several common mistakes in security safety arguments. The first is unstated assumptions. For example, the claim that displayed vitals are accurate may assume that the communication channel is trustworthy, but that assumption is never stated or even defended. The second is a circular reasoning. A system is not secure simply because it passed a security test. The scope of the test matters. If the test did not cover the relevant attack path, it does not support the safety claim. The third is confusing compliance with assurance. ISO 27001 certification may show that an organization has an information security management system. It doesn't automatically mean that safety-relevant threats in a specific cyber-physical system have been addressed. And the fourth is ignoring undeveloped node. Making a sub-goal as undeveloped is acceptable during analysis, but forgetting it, leaving a gap in the safety case, of course, is not acceptable. The fifth is stale evidence. Security evidence ages quickly. A penetration test from some time does not demonstrate the current security posture of a connected system. For example, 2 years ago, a penetration test does not demonstrate the current security posture because threats evolved and there's new vulnerabilities and so on. So these mistakes are partly caused by deeper practical challenges. Security-informed safety is difficult because it crosses disciplines. Safety engineers often think in terms of failure modes, hazard analysis, and assurance cases. Security engineers often think in terms of attack trees, adversary models, vulnerabilities, and exploitation paths. Few people are fluent in both. And standards also lag behind. Functional safety standards predate many modern connectivity assumptions, and information security standards may ignore physical safety consequences. Industrial automation security standards are improving the situation, but adoption is still uneven. Another challenge is that security evolves. While safety cases are often static, a safety case may be validated at a point in time, but vulnerabilities continue to emerge. Patching may improve security, but also change the certified systems. And finally, there are cost and legacy problems. Retrofitting security into deployed safety-critical system is expensive and risky. Operational technology lifecycle may last 15 to 30 years, which is a lot longer than typical IT refresh cycles. And finally, regulatory drive. Several regulatory developments are pushing organizations towards integrated security safety thinking. The EU Cyber Resilience Act introduced mandatory cybersecurity requirements for products with digital elements, including IoT devices. The UK PSTI Act bans default password and requires vulnerability disclosure for consumer IoT. The FDA pre-market cybersecurity guidance requires medical device manufacturers to submit cybersecurity documentation as part of the safety approval. The IES 62443 provides a security standard for industrial automation and control system and can be aligned with functional safety requirements. And UNIS WP29 requires cybersecurity management systems for type approval of road vehicles. The direction of this regulatory drive is quite clear. Cybersecurity is increasingly treated as part of the product assurance, not as a traditional add-on. So to summarize, the main message of this lecture is that security-informed safety treats security threats as part of safety assurance. Assurance is incomplete without accounting for security threats. Attacks are not the same as failures. Adversaries violate the independence and randomness assumptions of traditional safety analysis. And the causal chain is vulnerability, exploit, compromise, hazard, and harm. And the safety cases use CAE to build structured assurance argument, while the GSN provides graphical notation for making those arguments explicit. Security-informed hazard analysis extend traditional methods by treating attack paths as hazard source. Finally, regulations is catching up. All of those regulations point towards integrated security safety thinking. And the key takeaway is this. In connected cyber-physical systems, we cannot claim that the system is safe unless we understand how security failures could change its behavior. Thank you.